Brian McNamara, who is faculty at the University of Waterloo, joined from the Determinant Institute, and one about supermassive black holes and following galaxy formation.
Okay, well, thanks for inviting me up here, Phil. It's always a pleasure to come to Toronto. It's a city, since I moved up here, I've taken quite an affection to it. It makes it a lot more fun to be here and have an opportunity to talk to you folks today. What I'm going to talk about is a problem that I've been working on now for about 10 years with several collaborators, postdocs, and students. And I'm going to highlight the early part of the talk is going to be reviewed, just to get you up to speed on what we've learned in the last 10 years about feedback and the role that black holes play in galaxy formation. And then I'll show some new stuff that I've been working on with a student, and Cliff Patrick, and my ex-postdoc, Tim Cavagnolo, who's actually in France now, he's no longer at UW, and several other people, and then Paul Molson and Mike Wise have been longtime collaborators, but they're pros, so I don't need to give them any publicity. So the first slide I'm going to show here more or less summarizes the gist of this talk. This object will pass through the talk on several occasions, but the picture provides a nice overview and sort of gives you a location in space of where we are. I see some people squinting. It's a bit of a, if the lights can be turned down. Yeah, that's much better. So what's shown here is an image of a galaxy cluster at a redshift of about 0.26. It's known by this name up here. I won't even repeat. MSO735 is how I'll refer to it. And there are three, this image is a composite of three different telescopes. There's a visual image, or a near IR image, taken with the Hubble Space Telescope, in which you can see are these galaxies here. All of these objects are galaxies sitting in this cluster. It's a fairly rich cluster. It's got a temperature, a gas temperature of about between 5 and 6 keV, so it's massive. You can see lots of galaxies in there, and then what you see is this blue haze. And the blue haze is the X-ray emitting gas that's been heated up to roughly the virial temperature of the galaxy cluster. And of course, most of the baryons that live inside galaxy clusters don't live in the galaxy. They live in this hot haze or hot halo of gas that surrounds the galaxies. And all of this is sitting presumably in a big dark matter potential lobe. In addition to that, you can see this red structure. This is a 327 megahertz image that was taken with a very large array in New Mexico. And you can see that there's this very large structure. This puts a scale on. This is a very large radio source. So it's from here to here, it's roughly 200 kiloparsecs long. And you can see also that this source sort of bends around and leads back to this big giant galaxy that's sitting at the center of the galaxy cluster. This is in the general class known as CD galaxies. They're the largest galaxies as a class in the universe. They, by virtue of being the most luminous galaxies, they almost certainly harbor the biggest black holes in the universe. And we believe that in this galaxy, the amount of light being emitted from this galaxy suggests that this guy has a black hole that's several times 10 to the 9 solar masses, or at least greater than 10 to the 9 solar masses. And I probably won't get to it today unless I'm asked about it later. But there's also tentative evidence or indirect evidence that this may have a very, very large supermassive black hole. In any case, all the objects that I'll discuss are these bright luminous galaxies sitting at the centers of clusters, and they have large black holes at the centers of their galaxies, presumably. What you'll also notice, it's a little harder to see here, but you'll see it better in other systems. There's also giant holes located beneath these radio lobes. And they're quite remarkable because the data are consistent with these holes having been excavated out of the intercluster medium. In total, about 1 trillion solar masses of gas was excavated out of this cluster and pushed off to the side in these cavities or rims right over here. And one of the things that we get, two of the things that we can measure quite accurately with an X-ray telescope. So the X-ray image was taken with the Chandra X-ray Observatory. It's got very, very good spatial resolution, so we can image these things and really detect the structure. 10 years ago and before, almost everything we took with an X-ray telescope looked fuzzy because the optics, it's very hard and expensive to build subarc second optics. And Chandra is the only subarc second X-ray optic that's been put into space for scientific use. And so we can detect these cavities in many systems. In fact, I'll show data from several dozen systems that have these cavities. And the interesting thing about them, apart from the fact that they're beautiful and they're kind of gee-whizzy, I mean, a trillion solar masses of gas is a lot of material to push away. You could fit 600 Milky Ways into those holes and so on. That all sounds great. But really, the thing that's of scientific interest is you can use that to estimate, in fact, I would say almost measure, the total amount of energy that's being pumped out of the black hole at the center. And the reason is we measure with high accuracy the temperature and density of the gas surrounding these things. And so by measuring the volumes, we get a good estimate of the PD work that's done as the radio source displaces the gas. And the thing that isn't surprising is that what we find, of course, is that these radio sources are mechanically very powerful. What is surprising is just how mechanically powerful they are. And they tell us a couple of things. They probably solve an interesting mystery known as the cooling flow problem in clusters, which I'll describe in a few minutes. And what makes it more broadly interesting is it's one of the problems that we have with galaxy formation itself, and that is there are too many of the baryons in the universe are hot and have collapsed into galaxies, and something is keeping it hot. And now one of the key mechanisms for doing that is AGN feedback. So I'll talk about that throughout my presentation today. And I'll also talk about this object in particular, because one of the interesting things about it is that this is a CD galaxy. By virtue of being that powerful, this is 10 to the 62 ergs. Okay, so the total energy, we've gotten new data on this thing, and the energetics all hang together pretty well. There's a big shock front in front of this. It's about a Mach 1.35 shock front, but we see the temperature jump behind this thing very clearly. We measure the energetics pretty accurately, and they come out to about 10 to the 62 or so in energy. And just to put that into some perspective, that would correspond, if you did this by accretion alone, that would correspond to accretion of about between 3 and 6 times 10 to the 8 solar masses of gas onto the central black hole to produce this just by accretion alone. And it turns out that this galaxy doesn't have a whole lot of gas in it. And so one of the things I may get to at the end, if there's time, is I'll put forward the idea that maybe it's powered by spin. But even that has some issues. And one reason why spin is interesting is that if you take a 10 to the 9 solar mass black hole and spin it up with a spin parameter of about unity, you get about 10 to the 62 ergs of energy. Okay, that could just be a coincidence, but certainly energetically, it's potentially feasible to do that. So I'll talk about that today. One of the other things I'll talk about is the evidence that these things are actually punching star formation in the centers of systems like this. And I'll point out that there are systems unlike this that have star formation at very healthy rates, several tens of solar masses per year. And I'll look at the gas properties, and there's some results, some new results that we just came up with that look pretty interesting, and I'll discuss that about the gas properties. I'll try to argue what isn't powering them. I'll suggest spin may play a role, but it's very speculative. I'll say that right at the outset. And then at the end, if there's time, I'll present new evidence that we have that these things are driving very large-scale metal-enriched outflows into the intercluster medium. So, by way of history, there's this problem called the cooling flow problem that goes back about 30 years now. I think it really got was first realized in the late 70s by Len Cowie and Andy Fabian, Paul Nelson, and others. And the problem was that in the Perseus cluster, the gas density, the thermal emission from the hot cluster gas was very high in the center. Okay, the X-ray power coming out of these systems ranged between 10 to the 44 and 10 to the 45 ergs per second. And they had a very steeply increasing X-ray gas density. So what this shows is a three-dimensional plot of the center of a cluster that is not Perseus, but it's something like that. At the base here, just to scale it, maybe about 100 kiloparsecs across. And what you see is the X-ray emissivity increases dramatically in toward the center, where there's always a CD galaxy sitting at the center. And because the cooling time scales as 1 over the density, and the emissivity scales as the density squared at the centers of these things, it was thought that the gas had to be cooling out at a very high rate. At least it was losing energy at a very high rate. And if you take the total gas mass that sits in this peak here, where the cooling time is of order several 10 to the 8 years, and by the time you get out to the edge here, it's certainly less than 10 to the 9 years. You take the mass, divide by the cooling time, and you get cooling rates that are between tens to thousands of solar masses per year. The problem was that, so that suggests that the gas is cooling down, it's accreting onto the galaxy, it should be forming stars at a healthy rate, a comparable rate if it's in any kind of equilibrium or in a steady state. And what we've found over the years is that indeed there is star formation in these systems. This is a picture of Perseus. Perseus is experiencing star formation at a couple of tens of solar masses per year, and it has these beautiful filaments of what are likely to be cooling gas, or at least it's gas at 10 to the 4 degrees emitting the H-alpha line, and sinking down onto the galaxy and forming stars. But there's a big gulf between the inferred accretion rate just from thermal emission of the X-rays and star formation. And this is a problem that goes back quite a long time. It became rather nasty at one point. I got out of the game for a while because it wasn't interesting. In the late 90s, we had no new telescopes, so I went off and did other things. But then I came back to it. I was at the time working with the Chandra Observatory. This is a problem I was interested in. And a couple of things happened right when XMM Newton and Chandra were launched. XMM Newton was launched within months of Chandra, and the difference, this is an X-ray telescope launched by the Europeans. It's a light bucket. It's got fairly poor spatial resolution. It has 3 to 5 arc-second optics, but it's a big bucket. It collects a lot of light, so it's good for spectroscopy. Chandra has smaller optics, but finely tuned optics, so we get sharp imaging from Chandra. And there were 2 discoveries that kind of changed the nature of the problem. One was that the spectroscopy, I won't go into the detail, but basically, if you're cooling gas out of the intercluster medium, once the gas drops below about a kPb and a half or so, most of the losses come from recombination lines in the soft X-ray band. And you expected very strong soft X-ray emission, but that emission was absent in the lines. And the lines indicated that the cooling rates were vastly less than what you would get by just taking the mass and dividing by the cooling time. And the second thing we found, the first one being Hydra A, was that there were these giant cavities that were being created by the radio sources in the centers of clusters. And we just were able to put the 2 things together. The main contribution, I think, that we made at that point is we realized we could use this to measure the power output from radio sources, because it had long been an issue. We knew radio sources lived at the centers of these things. People had suggested that maybe AGN feedback was stopping the cooling, but the problem was that the radio sources were relatively weak. And it's been known for a long time that, of course, they're mechanically dominated. What we didn't realize was just how mechanically dominated the radio sources are. And when you do the energetics, as I'll show the evidence later, it turns out that there's enough energy being pumped out in these things to quench the cooling flow, or at least to offset the radiative losses. The other thing we were fooled by is that the radio sources tend to be, well, in addition to being weak, they're not always on. Whereas the X-rays are constantly, energy is flowing out from X-rays constantly. And one of the things that these halos do is they leave an imprint. The cavities are imprinted on the halo, and we can actually see them as they rise into the intercluster medium. And so, they will persist, whereas the radio sources will fade out. And so we can actually get a sense of the history of heating in these systems. And so the next task was then to show that this was a plausible explanation for why the gas wasn't cooling as rapidly as we thought. And so this is where this idea of AGN feedback came in. And when I talk about feedback here, what I mean, feedback has become sort of a buzzword, and I mean it more or less in its purest sense, and that is that the gas that is fueling both star formation and presumably the black hole, which is pumping out this energy, is also the stuff that's being heated by the same thermostat, which I would argue is the black hole at the center. Okay, and so this is you know, in what it looks like is that this is a reasonably finely tuned feedback loop, and I'll show you the evidence for that. Is that the AGN mechanical power certainly is enough to compensate for the cooling rates, but you also see more power in systems that seem to be cooling at a higher rate. And all of these systems, interestingly enough, still have very short cooling times, and that's hard to do without postulating the notion of feedback. So this has now become known as radio mode feedback. We didn't dub it radio mode feedback. That was done a little bit later by galaxy formation modelers who saw some of this stuff, and it really took off in the galaxy formation community. It's called radio mode feedback, which I think is a horrible name because the radio has nothing to do with it. As we'll see, the radio flux coming out, the actual energy in radio photons is being between 1/100th and 1/10,000 of the total energy. So it's really a mechanical feedback more than it is radio mode feedback. And just to put it in sort of bigger perspective, this mode of feedback has now been used to at least to explain or attempt to describe a problem that has existed in the lambda CDM model for some time, and that is that when you predict from lambda CDM models that you should get essentially a power law distribution of galaxy magnitude. So what I plotted here, what I haven't plotted, I'm showing this is from Bauer. This is the luminosity function of galaxies. It's essentially the luminosity per unit volume from galaxies versus their magnitude. That's the number per unit volume, per unit magnitude versus their magnitude. And stuff, perversely, that has a bigger negative number is actually brighter. And so what you see is that when you get to bright galaxies, the biggest ones, the ones that I'm showing here, their numbers tail off, and their luminosities also tail off much faster than lambda CDM predicts. And so now the leading explanation for this is that galaxy formation in big galaxies has shut off at late times, and that's largely due to this so-called radio mode heating. And so that's an argument for feedback. And there's also the fossil evidence, possibly fossil evidence for feedback, which is this famous relationship between bulge mass and supermassive black hole mass, which suggests the possibility that this relationship was imprinted by feedback, although it's by no means proved that that's true. There are other ideas out there that circumvent this feedback. So it's had fairly broad consequences. There are other things as well. You know, this stuff I've already discussed. The excess number of baryons is just basically a summary. But the other thing is, once you start measuring the amount of energy coming out of a black hole, there are many other problems that you can start to address, like the composition of radio sources and just how much power is coming out, which can be used to study feedback on larger scales. There are a number of interesting consequences for this, but basically the measurement we get is how much mass is falling into the black hole, or at least an estimate of it. We get, you know, roughly how fast the black holes are growing, and certainly we can do the energetics to a very high accuracy. In addition to, you know, explosions or these outbursts that are seen on galaxy scales, there are these large-scale outbursts. The one I showed earlier is not unique. They're rare, but not unique. This is an object called Hydra A, which is a famous radio galaxy. This is an X-ray image. If we were to see it in the visual, there'd be a galaxy sitting way down here. Okay, and what you can see are these two little inner cavities here. These were the cavities that I showed a few minutes ago. They were the first ones we saw with Chandra. When we got deeper images, what we noticed is that these were just the tip of the iceberg. Okay, these were about 10 to 59 ergs, the amount of energy being pumped out in these. But the entire central region, notice the scale bar on here, of this X-ray cluster is filled with cavities. And so if you take within about 500 kiloparsecs, if you look at the volume filling of these things, it's about 10% is in holes. So it's got the consistency of Swiss cheese. And what you can see surrounding it is a shock front, which if I can get this thing, this thing here is a shock front, a weak shock front, but it's a very large volume. So the amount of energy involved is quite large. And if you look in the radio, this is at high frequencies, this is at lower frequencies, so this is 370 megahertz, and you can see that the radio source fills these cavities like a glove. So it's quite clear that the energy that's being pumped out into these things has its origin right down at the center with a black hole, and the numbers can be very large. In this case, it's 10 to the 61 hertz. And we actually, from the decrements, the amount of flux that's lost in these cavity systems, we can actually attempt to build a 3D model, making some assumptions about the overall distribution of the gas. And this is a nifty little cartoon showing an observer's view, I don't know, a theoretical model or a semi-empirical model of what this cavity system looks like coming out of Hydra A. But it's a very big thing. And one of the really noticeable aspects of this is this guy is just on. It's not like it's popping off now and then. This guy is on, and it's been on for the last 500 million years or so, and it just or longer, and it just keeps going. So this thing is on. It's constantly pumping energy, at least in the last 500 million years, into the cluster. So how do we get the power? This is the only theory you'll see in this talk. It's a very simple theory. The idea here for measuring the jet power is quite simple. Okay? It's boring from a theoretical physicist's point of view. It's great for us observers because it's so simple. It's fairly hard to argue with. So the idea is that the nucleus pops off. This material goes out into the intercluster medium and blows away the gas. It takes 1 PV of energy to inflate the cavity. It's just like inflating a balloon against the surrounding pressure. There's a shock front that pushes out around it. We get the total energy, just to inflate it from PV, just by measuring the size of it. We assume that it's a spheroid. And that tells us the energy. But then what we've also noticed is that these things are persistent. Okay? They don't just inflate and collapse. You saw before that the cavity system in Hydra is several 10 to the 8th years old. So these things just don't fall apart. They actually persist and are able to rise at least 1 diameter before they break up or just sort of fall into the haze. And so the total energy that you get just depends on whatever's filling it. They're roughly in pressure balance. They can't be strongly overpressured because otherwise it would drive a strong shock, and we don't see that. And when you do the energetics, just using the shocks alone, you get numbers that agree to within a factor of 2 or 3, which is, probably more of an indication of the accuracy of the method. So we get the total energy. We get the time scale, both from the rise time, assuming these things, the dynamics are dominated by buoyancy, and we also get an independent one from the shock. And the bottom line is, by just applying this to these systems, you get numbers that range between 10 to the 55 and 10 to the 62 ergs, which are very large indeed. So one of the things that we can get out of this, probably the most basic observational derivative, let's say, of this. And so up here you see there's a lot of these systems, which are shown at the top. But we'd like to know how much energy is coming. We can see radio waves across the universe. Okay? We can only detect these systems in a limited number of clusters and ellipticals, even though there are several dozen that have been discovered. What we would like to study, for various reasons, we would like to study the power output of radio sources over cosmic time. One, because it helps us understand the growth of galaxies. There are many problems that can be solved here. So out of this, what we did is set out to derive a scaling relationship between jet power, that is, as we measure using the cavities, and radio power. And this shows it for 2 frequencies, both at low frequencies, 200 to 400 megahertz, and 1.4 gigahertz. And so these are useful for many of the, should be useful for many of the radio surveys that will be coming online in the next several years, including LOFAR. And what you can see is there's a trend between jet power and radio power, or cavity power as it is shown here. And it scales as luminosity to the 0.7 power, which interestingly enough is fairly consistent with what you expect from simple models for radio lobes in radio galaxies.
How do you get the lifetime?
The lifetime is got by assuming that these things are dominated by buoyancy, or you can get the age of the shock from the Mach number. You can trace it back to the nucleus of the shock.
Right. In most cases, you really have that?
No. We had that in a small number of cases, so we're assuming here that these are dominated by buoyancy. And so in any case, what you see here is this trend, but you also see a very large scatter, okay? At any given place here in radio power, you can have a very large spread in mechanical power, and this is almost certainly not just due to aging the radio source. This is probably intrinsic. I won't talk about that, but I would argue that it's probably intrinsic. But the other thing that's interesting to see, you can see why this cooling flow problem that has been sitting around for a long time was so hard to tackle. If you come over here, right here, this is 10 to the 40, if you can't see that here. So this is 10 to the 40. And if you go up this line, okay, and you look over here, what you see here is that this is 2 orders of magnitude larger. So that the boost you're getting in mechanical power over the radio power is on average about a factor of 100 at 1.4 gigahertz. But there are systems, like this guy here, that is between 4 and 6 orders of magnitude higher than the radio source. So what this means is that radio faint, or fairly radio innocuous galaxies, let's say, can be as powerful as quasars. And we just didn't know that before. And when you fold all this through, it turns out there's enough energy coming out of these things, almost certainly enough energy coming out of these things, to compensate for the radiative losses in these clusters. So now, what is the evidence for feedback? I suggested it's feedback, and there are sort of 3 pieces of evidence that this really is a feedback loop and not things just popping off. The first piece relates to the cooling time. So we can measure the density and temperature of this gas very accurately, right into the center. And what we find in these systems, regardless of the power of the jet, okay, systems that have 10 to the 62 ergs being pumped out, still live in halos where the cooling time is less than a gigayear. And in many cases, it's only 500 million years in the center. If these things were not regulated, this is hard to imagine here. Okay, so we're pumping all of this energy in, yet most of the gas is cooling at a very high rate. If this thing wasn't in some kind of a feedback loop, what you'd expect to happen is the cooling time would go down, the gas would cool, flood the nucleus, it would get blasted out, and it would drive the cooling time up to whatever the natural time scale is, cooling time scale of these clusters. And it doesn't. What you see is that the cooling time is very short at the center, regardless of the jet power. And that means that in order to keep that stuff at that level, okay, you need to keep pumping. You need to keep hitting this thing with power from the AGN in order to maintain this stuff at this level and not have runaway star formation at the center, which you don't see in many of these systems. The second piece of evidence shows this cavity power here versus the cooling from the ICM. I'll just call this a cooling parameter. This is the amount of energy that has to be offset by the AGN to stop cooling, and this is the power out. And what you see here is an envelope that shows that objects that are more powerful in the radio or in cavity power are also have the highest cooling rates, and the objects that need less power to offset cooling in their halos have lower power jets. And it's almost certainly not due to differences in, say, the black holes, because they all should have very large black holes. These are bright systems. And the other thing, this is the plot that also shows that there's enough energy. What's shown here is 16 PV, 4 PV, and 1 PV of energy. We think 4 PV is what you'd expect from each cavity if it's filled with a relativistic plasma. And what you can see is, on average, these systems have enough power to offset cooling. There are some systems that seem to be underpowered, okay? Some are overpowered. I will argue that there's tentative evidence that the underpowered guys are the ones that show evidence for star formation. The other thing that we found just the last couple of years is really interesting. We found that there's a star formation threshold in these systems. So there is star formation in these systems. It's not as high as you would expect with pure radiative cooling refueling it. But there has also been some disagreement about where the cold gas that's seen in these systems comes from. Some have argued that the gas has, basically just been dropped in from an interloper, a merger, or whatever. And I would argue that that's very hard to explain because many of these systems have molecular gas masses that exceed 10 to the 10. In some cases, dramatically exceed 10 to the 10. And there are no donor galaxies in the cluster to do that. But more interestingly, we found this threshold for star formation in these systems. So I won't explain this because it's sort of complicated, but basically it's a color gradient thing. It's a measure of the blueness of the center of the galaxy. And the bluer it is, the more star formation there is. And up in that direction is blue, and down here is red. So anything above the dashed line is blue, and anything below is red. And red means old, it hasn't experienced star formation. Blue means it's forming stars. And it's plotted against the central cooling time, which we measure in the X-rays. And what you notice here is that these guys with long cooling times are universally red. And you move down here to 10, this is 10 to the 9 years, 9 times 10 to the 8 years, dot, 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 and then bang. All of a sudden, when you get a cooling time that's about 5 times 10 to the 8 years, these things light up like Christmas trees in the center. They start forming stars. They don't all, notice there are some red ones, but only systems with short cooling times show up in the blue, show up as being star formers. And a similar relationship was found also by M. Cavagnolo and company in H alpha, where you see a very similar threshold, although they expressed it in entropy. They're essentially the same thing. I prefer cooling time because for me it's a little bit more physical, I think. So basically what we've shown is that the star formation of these things really is linked to the cooling atmosphere. And it adds, I think, to this notion that these things are basically set up in a feedback loop. Yeah?
So all the shortest cooling time ones are red, right?
The long cooling times are all red.
No, but if you look at the very shortest ones are also all red.
There are some, yeah. Right, these are elliptical galaxies.
Yeah.
They're probably elliptical galaxies. And so, I haven't shown this, but we also have, there are probably 3 things that determine this, not just cooling time. I think cooling time is the key thing. The other thing is it sitting right at the base of the atmosphere? And if they're not, they never have star formation. And the third thing is, frequently these things have very high-powered jets in them, which are probably shutting cooling down. So for example, MS0735, that first one that I showed you, has a cooling time that's right on this ledge here, but it's red. Okay, so it looks like the thing. Those are 2 other parameters that are causing scatter in this thing. Okay, I can't say that with any certainty because that's only sort of a 2 sigma result, and I'm not showing that.
I think you were mostly asking about less than 10 to the 8 years, right?
Yeah, right down in here.
So 3 or 4 there that are really short.
Right down in here, right. And so those are in the coolest systems, and they also tend to have fairly significant, they're cooler systems, they have less mass, but they also have radio sources that are on that are probably compensating for the cooling. I can't say that, as a fact, but there's evidence to suggest that that's what's going on. So the sort of cartoon sketch that seems to be falling out of this, it's not perfect. This is sort of my 90% confidence sort of sketch of what's going on. And that is, if this is the plot of jet power versus cooling luminosity, what we get are these systems. This is quenching, sort of balancing, heating, and cooling. The GEs, the giant ellipticals, which were some of the ones that were over in that very cool section, because they're smaller systems, they have shorter cooling times. They're almost all old, red, and dead, as they say. And it turns out that when you do the power analysis, there's enough power coming out of the AGN to quench the gas. These, in the clusters, I would call these struggling, okay? Because a lot of them have enough power to quench star formation. But some of these, there's so much gas and the cooling time is so short in the center. Well, the cooling time is short enough in the center that I think the AGN are struggling to stave off star formation, and indeed, in some of those systems you see star formation. So that's the sketch. That's not scientific fact, but that's about my 90% bet about what's going on. And the data just keeps, I think, piling up and supporting this. There are other studies that have shown very similar things. Okay, so what I want to do now is switch gears and ask, how are these things fueled? Okay, it turns out the gas properties and things are very interesting. There's a couple of possibilities. One is that these are accretion-powered systems, so there's cold gas. The other idea is that hot gas is secreting onto the black hole. I will argue that this is almost certainly wrong for the powerful systems because there's just not enough gas there to do it. The other possibility is spin, and if I get time, I'll talk about that, but I don't know if there will be. I may just sort of leave it out as a possibility and move on. But Bondi accretion, I think, is problematical. Okay, so this is accrete. The idea is that there's essentially a spherical halo of hot gas that's in balance by gravity of the black hole at the center. The matter accretes quasi-spherically under the center of the black hole. The accretion rate scales with the square of the black hole, as you would expect, and the jet power is some fraction of m dot times c squared, where epsilon depends something on the spin rate, and eta is just an efficiency factor that accounts for the fact that the gas has angular momentum. It may also experience outflow and so on. And I will argue here that that may be important in weak systems, but in powerful systems, there's just not enough gas surrounding the black hole to power these very powerful systems. And that's shown here. This is a plot of the jet power over the power, the Bondi power, assuming the temperature and density of gas near the center of the cluster. Now, I will caution that the gas is unresolved. Okay, the Bondi radius is unresolved in almost all of these. But you cannot just arbitrarily increase the density and decrease the temperature without paying a penalty. There will be emission from that because it will emit thermally, and it can emit very strongly thermally because as the density drops, the emissivity scales as the density squared. And so you will see emission from these things. So that's one caveat. But in almost all of these systems where, even if you account for that, if you allow the density to increase quite strongly in the centers of these systems, what you find is that these guys up here are just vastly too powerful to be powered by spherical accretion in the hot atmosphere. It's possible that these weaker systems, like M87 and so on, could be powered by Bondi accretion. But even those systems apparently have problems because there's angular momentum that has to be removed in order to get the gas down. These things are never perfectly spherical. And the interesting thing here, the reason why I bring this up is if you look at almost all of the models that have been put out, essentially all of them, Kernquist, Croton, all of these guys, all assume that these things are driven by Bondi accretion, and I would argue that that's almost certainly wrong. Or, if it is important in some of these systems, it requires two separate mechanisms to explain these. And that's, oftentimes that alone is troubling if you can get away with one.
So I remember some old results by actually guys at Stanford.
Alan?
No. Those for lower luminosity systems?
Yes. So at this level, it's not in conflict with that. Those are all lower luminosity systems. But I have my doubts that there's this relationship between the two. We've measured a lot of those, and they're very different jet powers. Okay, so the other possibility is cold gas accretion, which I'm sure you've all seen. And the key here is just, again, you can get, if you dump matter onto a black hole, you get energy out. And the important thing here is that these things, a lot of these systems are harboring a lot of cold gas. So I argued earlier that cold gas is almost certainly coming in from the hot halo based on this threshold effect. But the other thing is there are no donors in clusters of galaxies that have this much gas. And this is the amount of gas that's sitting in some of these systems. So it almost certainly seems like it's coming from the halo. And what you can see here is these are also big star-forming systems. Many of this is just a rogues gallery of clusters that have star formation in the UV. These are UV images, so it shows there are hot stars forming in these systems. This is a CO image from Salome and Combs. This is from a cluster called Abell 1835 that has about 10 to the 11 solar masses of gas sitting down in its center, and it's forming stars at a rate of about 100 solar masses per year or so. So why not the gas? There's an enormous amount of gas in some of these. Maybe that's what's fueling the AGN. So I did this work with a student of mine, Nina Mohanazadagan, and we just said, well, let's plot the molecular gas mass versus the jet power and see if there's a relationship between gas mass and how much power is coming out of the black hole. And this is what you get for these large systems. Basically, over this range of jet power, okay, so you see 10 to the 46, so some of these are pretty powerful, down to guys like M87, which are much lower power, you don't see much of a trend. Okay, statistically, there's no trend there. where I have a student, an undergraduate, who's extended this down to nearby systems that are lower power, and there probably is a weak trend between jet power and molecular gas mass. But the interesting thing is there's this huge scatter. So there are these systems up here. All of these systems are big star formers. They have a lot of gas, well over 10 to the 10 solar masses of gas. They're forming stars like gangbusters. They have fairly powerful AGN, there's no question about it. But there are other systems like MSO735 that has a lower limit of a couple 3 times 10 to the 10, and it's probably considerably less than that in this guy. Yet its jet power beats all of these. And there are several others here that are in the same boat. So there's no real strong, there's no trend in this system between molecular gas mass, and there's a huge scatter in jet power depending on the mass, which was a bit of a surprise. This is a little bit more complicated, although not much. Okay, this is molecular gas mass here over an efficiency parameter. And what this is, so this is the jet energy that we measure directly from the cavities, divided by 0.1 times the molecular gas mass C squared. So basically, what this is this tells you, assuming that you get a 10% efficiency, jet accretion to jet power efficiency, which is the sort of standard assumption people make. This ratio tells you the number of pops, the number of outbursts you could get at that power, given the amount of gas that's sitting in these systems. So something that's down here would be a low efficiency system. In other words, a low fraction of the total gas mass is actually getting down into the black hole and feeding accretion. And these are the high efficiency systems. And in the case of MSO735, if you take its, what I think is its gas limit at face value, it implies that, nearly all of the gas, or at least, a significant fraction of the gas that's living in this galaxy had to stop doing what it was doing, fly down into the nucleus, land on the black hole, cause this enormous outburst, and they had to do so without forming any stars. So in this system here, it's forming stars at a rate that's less than a quarter solar masses per year, yet between 3 and 6 times 10 to the 8 solar masses of gas have to fly down onto that black hole in the last 100 million years to power the outburst. By contrast, these guys are all forming stars at rates between 50 and 100 solar masses per year. Okay, and so these guys have relatively, they're a low efficiency system, they have high gas masses, and they have a lot of star formation. But they're just not as powerful per unit mass. So it seems that in these systems, most of the gas is being consumed, perhaps by stars, or something is hanging that gas up and preventing it from getting to the nucleus. And in these things, they seem to be very efficient. These guys, by the way, are all either low star formers. This guy has a star formation at a rate of a few solar masses per year in a disk surrounding the center, but it's still accreting matter very efficiently down to the nucleus. These guys as well, this guy is not forming stars, Cygnus A is probably forming a few, and so on. These guys are almost Eulers. So there seems to be an inverse relationship between the amount of gas and the efficiency which gas is getting down to the center. And just to sort of put this in context, this is the global efficiency for galaxies. So if you take the slope of the Magorian relation, which is the relationship between black hole mass and bulge mass, you get a ratio of roughly 700 to 1. And what that means is averaged over time, for every unit of mass that fell onto the central black hole, 700 units went into star formation. Okay, and so you can see by that measure, these things are today very efficient accretors, and these guys are somewhere close to the global mean. So that was a bit of a surprise.
So for these higher luminosity sources, what do you know about the accretion distribution around the block?
I'll get to that. It's faint. You don't see any. So if you look at MSO735, we looked at it with HST and so on, it looks like just a normal nucleus. The only thing that's unusual is it has a bright H alpha cloud. But there's very little gas associated with that H alpha cloud. If I have time, I'll get into it, but I'm sort of running out of time. So anyway, why are these things lower accretion efficiency? It may be that the gas is consumed by star formation. It may be it's stalled in a disk. I don't know, maybe Norm has some ideas. I thought I would talk to you before I left about this. But I think ALMA will be a very interesting telescope to try to figure this out. I'm like 5 minutes away from finishing up, I think. So you said you want me to finish by 4, right? Okay. So I'm going to skip this. If you want to ask me about spin, I've got an argument. The argument is simple. There's not enough gas down there to to try to explain this, or I don't think there's enough to explain it, by accretion. And so why not spin? And so why not spin? It may be spin, but the big problem with spin models is that in order to get spin to work, you need accretion for most of these systems. And it turns out you need almost as much accretion to get spin, to tap the spin, as you get from just purely dropping gas onto the black hole. Okay? And so what we did is we took one of these new hybrid spin models, which uses this thing called the Blanford-Zemanek effect, which is shown here. The scaling for the idea with the Blanford-Zemanek effect, as many of you know better than I do here, I'm sure, is that you tap the power of the spinning black hole by applying a torque through the magnetic fields that are connected to a surrounding accretion disk and the ergosphere of the black hole. And that applies a pressure, so it's a squared here. This is V squared. That's a magnetic pressure pushing against the ergosphere. The amount of energy you get scales then as the black hole mass squared and as the spin parameter squared. And you can get a lot of energy out. And of course, but the problem is you just can't arbitrarily turn up the magnetic field pressure because you need a confining disk to anchor it. And it turns out that in most of these systems, most of the models that I've looked at, they're not my models, but I've looked at some, in order to be self-consistent, you need very high accretion rates on these things. So it doesn't really get around the problem unless someone can come up with a method of tapping the spin energy without having to anchor the fields to such big disks surrounding the black hole. And there are various ideas. The idea is that the magnetic fields may be plunging over the ISCO, the innermost stable circular orbit, and perhaps that anchors them and boosts up the magnetic field pressure. Maybe there's just some other mechanism. The bottom line is, if you scale this, so I won't even quote a spin parameter for these things. Good, I didn't put it up there. And the reason is, there are too many free parameters. You have to make some assumptions here. Because the magnetic field strength is a free parameter, we think we can nail down the black hole mass to some accuracy. These guys are 4 systems that have measured black hole masses, so they're all within the range. But really what we're measuring here is galaxy luminosity. It's not black hole mass. We have to keep that in mind. We're just using the Gregorian relation. But what we can do then is scale this up and say these things, assume that these things are being pumped out, power is being pumped out at the maximum you can get of J equals 1, and ask then how much accretion would be required to do that. And it turns out it's about 2% of the Eddington rate. And that, it turns out, is very close to what people think is this transition between being a quasar, where you have a thin disk that's radiating its energy through the normal processes of gas bumping into each other, known as alpha viscosity, and where you have a thick, an optically thin, geometrically thick disk that can couple to the spin of the black hole and drive a jet. And all of these things have jets. Some of them have point sources in the X-ray. Very few of them have point sources in the UV. They are consistent with these funny things called ADAFs, which are known as advectively dominated accretion flows. In other words, most of the energy doesn't come out as radiation, it gets advected into the black hole. This is very speculative, okay? But it does highlight, if this turns out to be true and we can find more of these, it does signal a problem. It's very hard to get gas into a black hole. Okay, it wants to sit in a disk. You're dropping something from orbit onto something the size of a grape. And if you want to get it to fall in straight, you have to be a very accurate shooter, and gas just doesn't do that. It ends up in an accretion disk, and once it ends up in a disk, it's going to sit there for 1 billion years. And in these systems, it cannot have sat there for 1 billion years. It had to accrete down in 10 to the 8th, in a couple 10 to the 8th years, and we know that very accurately. Okay, so I'm just now going to finish up with just a couple of cool new observations that I'm going to point out. Okay, we got this deep chamber observation of MSO 735. It went 500 kiloseconds. We confirmed these big cavities that are sitting in the cluster. This is this guy I showed right at the beginning. It has a beautiful shock front around the edge, which you can see here. This big elliptical thing. It really looks quite classic. Okay. But the interesting thing, one of the ideas we thought might be powering this is, maybe 2 black holes came in and somehow, some matter fell in with it and, caused these jets. The problem with 2 black holes is most of the energy goes out in gravity waves, but there are models around it argued that there may be a disk that came in with the black holes, and maybe that powered the original jets, which are 10 to the 62 ergs. But what we found in the new deep image, which it turns out we published a Nature paper on this in 2005, it was in there, in the data, but we ignored it because we were paying attention to this big 10 to the 62 thing. But there's these new cavities in the center now. They don't look real compelling from that, but they're there. And right here in the H-alpha emission, so this is the optical image, that's the galaxy, this is the H-alpha, you can see this dip in here, which is due to this cavity in here. It looks pretty innocuous, but that thing is 10 to the 60 ergs, okay? The pressure is highest right down at the base. So there's 10 to the 60 ergs coming out in this new burst. So this is this gas-dry, almost gas-dry galaxy that is now pumping out this new system. And to add a little bit of, a little extra evidence to this, the way we spotted this was not actually by the image, which looks kind of ratty. It's because there's this temperature, persistent temperature jump that we saw in the temperature profile. So this is the gas temperature versus radius. And you come out and bang, there's this little jump here. Well, I went back to the Nature paper, and sure enough, it was in the Nature paper. We didn't say anything about it. But there's this little hot region here that looks like a shock that's surrounding this thing. And the thing that makes this also interesting is it has a very luminous H-alpha system. It seems to have very little gas. And if you took its H-alpha and you were to predict how much CO would be there, because there's a correlation between CO mass and H-alpha mass, which is a different thing, you'd expect there to be more than 10 to the 10 solar masses of CO here. So I would argue that this thing is popping off, and it's probably just lighting this thing up very recently, and eventually that will die down into obscurity. That's a speculation. We'll see. The point is, this is an ongoing system. This thing is cranking out at 10 to 60 years. For those of you who have seen the Antiphadian's Perseus picture, this is still several times more powerful than Perseus, and it's a couple hundred times more powerful than, say, M87. So even though this looks innocuous, and it's only a few percent of this big outburst, it's actually quite powerful. In fact, it's powerful enough, that alone, to stave off star formation in this thing at the cooling rates that we estimate.
What's the size scale of that cavity?
The size scale of that cavity is about 20 kiloparsecs or so. And finally, I just wanted to point out a new result from my graduate student, Cliff Kirkpatrick. He's looking at a lot of these systems with cavities. And we're using iron, the metallicity. One of the other things that you get out of these X-ray pictures is not just the temperature and density, but you also get the metal content of the gas. And one thing that you find in these systems is that when there's a big CD sitting at the center of the halo, the gas becomes very much enriched at the center. It's a factor of 2 or 3 times more enriched in heavy metals than the surrounding gas. And these metals come from just normal stellar evolution. The stars are pitching out metals as they evolve. And one of the tracers, one of the questions is, are these driving outflows? Are they taking gas from the center and pulling it out? And for us, the metals serve as a tracer of the gas and maybe moving. And so what's shown here is this is a rendition of the metallicity of the center of this galaxy cluster. And basically, the stuff that's in yellow here is the highest metallicity, and this stuff out here is lower metallicity. And what you can see here, this trace here shows the 1.4 gigahertz radio emission from these cavities right here, and that bigger thing that looked like Swiss cheese earlier is this stuff right there. And what you can see is there's this little trail of stuff that's going up, that's iron enriched, that turns out to be about between 2 and 7 times 10 to the 7 solar masses of iron. And it's dragged this stuff out. Normally this stuff, this color, is all concentrated into the center where the galaxy is. So this stuff is being dragged out. It's quite a bit of mass. And we're seeing this now in almost all of these systems. In fact, what Cliff is showing, we hope to get a paper out soon, is that the distance scales with the jet power in these systems. So it's direct evidence that there's not only this energy being put in, but it's driving outflows, and it's taking the metals that exist, that were born inside these galaxies, and it's distributing it throughout the intercluster medium, which I think is kind of cool. And I'm out of time. So, yep. So with that, I'll just summarize, and yeah, I'll take questions. Thank you very much.
So we have time for
Okay, questions?
So an extreme system, which might be a point way out the edge of most of the graph, would be as you saw.
Yes.
And Finkbeiner et al. Found these Fermi bubbles, which reminiscent of these other things, compared to full parsec scale, so much, much smaller. I was wondering if you guys had thought about that. Wondering if you could those issues and saw that you could harm Omenar if you go out to correlations. I don't even know whether or not it is.
Yeah, I hadn't really thought of doing that. The problem with the Milky Way's black holes is just so quiet. It's just not doing much.
Well, it's anomalous in many, many
Yeah.
respects, right? But,
These guys are.
there's this funny bubble feature in
Right.
there.
Yeah, I hadn't thought about that. But it's a good idea.
I think I already know the answer to this, but when you take the downstairs the steel masses, so first of all, do they look like they're in a disk with steel mass, or is it hard to tell?
It's hard to tell, but there are a couple of examples. So it turns out Hydra A, should I be saying this? I'll say it. Alistair just got some beautiful CO data showing the disk. There's a disk in Hydra A. We've known about this disk now since Susin's or in the 70s, right? There's an H alpha disk that sits right down in the center. There's also CO that's been recently detected. It hasn't been published, and it turns out there's a double hump structure in the disk. There's a hint of disk-like structure in some of these other things, but really the distances are so far, they're pretty far. It's pretty hard to say. I think Alma's going to be great.
Just for the obvious follow-up, if you had any spatial resolution, you can try to see these things still.
Oh, yeah, we've done that. Okay, and they, now, we have to play some games because we don't know exactly where the CO is, but they're consistent with sitting on the tank elevation.
So is it our spatial resolve?
There's only a handful, there's 2 or 3 that are spatially resolved, and the rest of them we have to infer the size, and by making reasonable assumptions, they sit on the tank population. So there's a paper by O'Day et al. Published in the last couple of years that shows that. But there's no evidence to suggest they don't.
But your one, the really big one, has very little gas.
Yeah.
You shouldn't expect any starvation. You don't see that.
Well, so here's the puzzle with that. So, we just put in a proposal with the plateau de Bourg interferometer to try to drive the limit down. The limit, it turns out, is not as good as it could be on CO. And the H alpha emission that I showed is consistent with other systems that have 10 to the 10 solar masses of CO. But every one of those have star formation at rates that are between 5 and 10 times higher than the upper limit there. I don't believe there's much CO in there. You consider these forming stars for the.
So then what's powering H alpha? It's not star formation.
There's, so the HST maps, which I probably have an image there that I'll just discuss, it show just, weak dust features that we would see in any elliptical gas. And there's no evidence of nuclear emission. It's not bright in UV. It's detected. The star formation rate is consistent with being 1/4 solar masses per year. The star formation rate from Spitzer is consistent with the same number. There's not a lot of evidence for gas in the Spitzer data. But it seems that if you take all that into account, I would argue that its H alpha emission is inflated. It's up by a factor of 10. And my speculation is that there is gas, but it's consistent with 10 to the 6. It could be several 10 to the 8 in there. The gas mass from the dust is consistent with a number as low as 10 to the 6. But if you run a shock through it and you start exciting the gas, you're going to boost the temperature, and we see a shock that sits right on the same scale as the H alpha. So I'm speculating that if that is just overluminous, the H alpha, and we wait, 10 to 7 years, and we'll be back to being bright but high and bright.
So the related question is, if you look at the spectral type of the galaxy, like there's plus A galaxy that has star formation ability.
There's no evidence for that.
Okay. Totally red.
It's totally red and dead. Kind of weird. We maybe, if we went out and, really, so that doesn't, it could be harboring star formation rate at a rate that's less than a solar mass per year. So there could be some star formation, but it's not. If it were at the level that we would expect in other systems, we'd see it. It'd be easy to see, but going off the wall, see it for the shortest range. It's weird.